Louise. Okay. So I have two rings. They're specifically designed just for this experiment. So they have the exact same
I have no clue why that fell.
gravity.
It's rolling wheels.
You're in physics. You're 11 weeks in and you have no clue why a cart fell off the table.
I stopped it right there. And it still fell down.
Anyway, back to our story. So these are the exact same width, okay? They're the exact same diameter. The masses are exactly the same, okay? One is the Lord of the Rings, one is a huge hockey puck. So, put it up here and let go of it. What's it going to do?
Roll down.
Will it undergo angular acceleration?
Yeah.
Yeah.
Yes. Why?
Gravity.
Because it's current.
Gravity's part of it, so you have
Force
force parallel pulling it down. That's part of it. Now, which direction is it going to spin? It's going to roll this way, but which direction is it going to spin on its axis?
Clockwise?
Is it going to spin counterclockwise or clockwise?
Clockwise?
For me, clockwise.
I mean, it depends on
For me,
Yeah.
clockwise.
Okay, but so
Yeah.
Right?
For us-
Yeah.
we got this action going. So, is a torque being applied to it?
Yes.
Yeah.
Why?
Because there's force and there's radius.
Yeah. So what's creating the force part of it?
Gravity.
No.
Force
Nope. Force parallel.
Nope.
Force normal.
Nope.
Force friction.
Yep. Okay. Because imagine that I put this, so if I put it like this, why doesn't it roll?
Friction.
There's friction. Friction's holding it in place. Gravity Mafia is trying to pull it down, but it's not going to go. So I put it this way, though, and it does roll. So the Gravity Mafia is still trying to pull it down, but the friction between this surface and the edge,
That's the reason it rolls.
that's the reason it rolls. So the friction is creating a torque that's going in this direction, but gravity's pulling it in this direction. Okay?
It makes a lot of sense.
So it goes like this. Now, if this was the magic frictionless puck, and this was the magic frictionless table, and I let go of it, what would it do?
Not roll. It'd just go down.
Yeah, it would just go like this.
Yeah.
Okay? It would not spin.
That'd feel weird.
So you have to have two things to make it spin. Force parallel and the force friction. Two things together. So I'm going to put them up here like this. We're going to have a race. Okay? Keep in mind, everything is the same. The width is the same. The mass is the same. The diameter is the same. They have the same, basically, coefficient of friction, so the frictional force is going to be the same. Everything's going to be the same. Question being is, though, which one gets to the bottom first? So you have three options. Number one is a tie, just because everything's going to be the same. Gravity doesn't differentiate. Everything's going to be the same. The hockey puck is going to win because you have an even distribution of mass. The Lord of the Rings is going to win because the mass is further to the outside. Okay? So those are your three options. Tie, hockey puck, Lord of the Rings. Those are your options. So how many vote? It's just going to be a tie. Nobody's on the tie train. Okay? Hockey puck.
I'll go with that.
1, 2, 3. Lord of the Rings. 2. Split
Wait,
on-
let me
on-
switch. Lord of the Rings, because I don't have a reason, but like I think I have a reason. Just go.
I'm
I'm gonna go with the ring.
You're back. You're on the
I'm
ring.
on the ring. I'm on the ring.
I was up feeling that. Like,
So now we have 3. We have 3 on the ring,
All right.
2 on the hockey puck.
I don't know, the ring just looks.
Are you guys still solid on the hockey puck?
I think, yeah.
I'm gonna just say.
You're staying.
I already picked it, so I'll
think
just.
Okay. All right. Are we ready?
Indeed.
No.
Indeed.
I'm there.
Frick.
Okay? Hockey puck 1. Now, let's talk moment of inertia. Right? Which one has the bigger moment of inertia? The ring or the disc?
The ring.
The ring does. Why?
There's nothing on the middle, so the radius.
All the mass is concentrated towards the outside. I
That's
equals
why I
mr
was gonna-
squared. Right?
Yeah.
So this has a bigger moment of inertia. This one, if you think about it, because it's a uniform density, on average, this is like saying all that mass is concentrated about halfway out. Okay? Yep, some to the outside, some toward the inside, but on average, it's like being halfway out.
Wait, so if this one was like the average radius of like the mass and that one, it would be the same?
Yes.
Okay.
So if you could shrink that down, where this would be that half size right there, then it would be the same.
Oh,
Okay?
that's pretty cool.
Then it would tell. So having this towards the outside, it's like having that aluminum rod with the brass weights. It's just like, imagine that you have all like a continuous system of those aluminum rods with weights towards the outside. So it's very difficult to get it to move. But what if I got them both rolling? If I got them both rolling, which would roll farther?
The ring.
The ring would. Because once you get it going,
It's hard to stop.
it's hard to stop it. Okay? Cool with that. All right. So now we're going to have a race between these two. Both contain 4 ball bearings. All right? So I'm going to... So I got
What's the
this.
difference?
You know what's the difference?
Okay?
We're gonna find out.
Well, no, what's the difference between the two things?
That's what I just said.
Okay. So this one was winning. Caitlin, open that up.
How do I open it?
Just unscrew this top. There's a wing nut on the top.
Maybe.
Come on, I got faith in you. Okay, now, I have 4 ball bearings, she had 4 ball bearings.
Oh, those
Hers was winning. Her ball bearings were closer to the inside.
moment of inertia smaller.
Moment of inertia is smaller. My 4 ball bearings are closer to the outside. So this is a bigger moment of inertia. So that one was winning because it was easier to accelerate. Because the moment of inertia was closer to the inside. Okay? Now, which one has more inertia?
Outside.
Wait, they're the same.
They're the exact same. Why?
Because they have equal mass.
They have the exact same mass.
But moment of inertia.
But moment
I
of
was
inertia is
thinking
not
of
the
that
same. Okay? Now, then you can have this action.
Uh-oh.
What the freak?
What? Oh, golly.
Oh. I see what he's doing.
Golly.
So in one situation, it rolls up the hill. One situation, it rolls down the hill.
Balls are all
the
on
balls
one
different
side.
radius?
Yeah.
Yeah, you have an uneven distribution of
Wait.
the ball bearings.
I hate that.
So this has all 4. So if I put that with that mass towards basically the upside of the center of mass, gravity pulls that harder and it makes it roll downhill. But if I put it on the other side, it makes it go down. So here's what I want you to get, is that if everything is the same, all the forces are the same, the one that's going to have the smaller moment of inertia is going to accelerate faster. Okay, if all things are equal, and that's a huge if.
But then it'll accelerate slower too, right?
But what?
It would accelerate slower too, or faster. Like it's accelerate, and then it would also accelerate and stop.
Yes,
faster too.
that's true. Okay, here we go. Back to the fret. Let's just keep it going.
I should have just said decelerate.
Rolling, rolling, rolling. Keep those rockets rolling. Slide. Okay. Okay, so we had the Lord of the Rings, and then then we had the hockey puck. Okay? It's two options. So this one had a bigger moment of inertia because on average the mass is closer to the outside. This one had a smaller moment of inertia. But which one underwent the bigger acceleration? The hockey puck or the Lord of the Rings?
Hug.
Hockey puck. So this had a bigger angular acceleration. This one had a smaller angular acceleration. So here's how you remember this, is that big fish have small eyes. Okay? So if you want a visual, so if it's a big fish, it has a tiny little eye. Okay? Now, the flip side of that is that small fish
How big eye?
have really big eyes. Okay? All right? So that's what we've seen so far. There's an inverse relationship between moment of inertia and angular acceleration. Okay? Got it? Good. Now, mathematically, and don't worry about writing this down. I'm just going to show you where this plays out. So if you have the Lord of the Rings, there's a very specific equation for calculating the moment of inertia of a ring. And that moment of inertia equation is I equals 1/2 m. I screwed that up. I put the mass on the outside. R1 squared plus R2 squared. Okay? So here's the ring, here's the radius, there's like R1, and then that outside radius would be R2. So if you put in the numbers for that ring, you have 1/2 times 0.65 meters, or 65 kilograms as your mass. And then you have R1, which is 0.070 meters squared plus 0.075 meters squared, and you crunch all of these numbers, and you get 3.4 times 10 to the minus third kilograms meters squared. Now, here's the problem with moment of inertia, okay? The problem with moment of inertia is that you calculate it, and it's a number, but it's tough to realize, hey, is this like a reasonable value? Mass, you say, oh, it has a mass of 40 grams. Okay, you all can get an idea of what 40 grams is. That's not much, okay? Versus 1 kilogram. Oh, okay, you get an idea of what 1 kilogram is. Or if you get a velocity that says, hey, I'm moving at 8 meters per second. Okay, yeah, you can visualize that. Okay, a really fast human could run 8 meters per second. It's tough to look at a moment of inertia number and go, oh yeah, I get that. I know what that feels like, okay? That's the tough part. It's one of the few instances in this class where you're going to get a number, and it's like, does it make sense? But you can get an idea certainly of magnitude. Because you got to figure if you have a small mass and a small radius, oh, that's not have a very big moment of inertia, okay? But if you have like Hank, there's a lot of mass, oh, that's going to be a bigger moment of inertia. So it's tough to look at a number and go, does it seem reasonable? But you can at least look at the magnitude of it and go, okay, hey, this kind of seems cool because it's a small number. Now, when you do the solid disk, and the solid disk is one of the more common ones we use a lot, the moment of inertia of a solid disk is 1/2 mr squared. Okay? So the reason that it's 1/2 mr squared, and if you ever take like Calc 3 or usually differential equations, you actually go through and you derive the origins of these equations. Don't worry about it for now, just accept it, move on. Okay? But here's a simple one to see. So if it's a solid disk, what we're saying is that on average, that mass is located halfway between the center and the outside. Okay? So it's like on average, this is where it is. Where if it was a thin hoop, okay, all of that mass would be located toward the outside and it would just be mr squared. So that's a kind of an easy conceptual way to understand kind of the origins of the equations. So if you come in here and you plug in these numbers, you get 1/2 that's the exact same mass, 0.65 kilograms. It has the same outside radius of 0.75 meters, and you square that, and you get 1.8 times 10 to the minus third kilograms meters squared. So mathematically, if you look at these two moments of inertia, the moment of inertia of the Lord of the Rings is 3.4 times 10 to the minus third. The moment of inertia of the solid disk is 1.8 times 10 to the minus third. Now, here's the other thing about moment of inertia. Don't, like on Monday, we're going to do a lab where we're going to try and calculate moment of inertia. There are no, like, moment of inertia probes, okay? Like, we can't plug something in and make it spin and go, oh, here's a measure of moment of inertia, right? Mass we can measure, time we can measure, distance we can measure, okay? We don't have probes to measure and validate these equations for moment of inertia, okay? But what we can do is say, oh, okay, right, this is what's happening. Here's this mathematical formula. We can predict what the acceleration would be, and we can try and verify it that way. But there's no way to directly measure moment of inertia. Okay, so here's going to be the next idea. So if you look at, we're going to make something spin. Okay, so yesterday we established that torque equals force times radius. Okay, so I'm going to completely contradict myself in about 2 minutes. But right now I want you to realize that if something's spinning, you are forbidden from using F equals ma. And here's the reason why. Is that if I take this wheel, okay, and I make it spin, okay, if I'm going to make it spin, what do I have to apply to the wheel? A force, right, and a torque, okay? I have to apply force at some radius. This is why you can't use F equals ma on spinning objects. Because if I apply that force way out here on the edge, I get a certain angular acceleration. Because if I apply that force out on the edge of the wheel, and if you look at torque equaling force times radius, that force, and if I multiply it by a big radius, is going to create a big value of torque. Okay? But if I apply that same force very close to the center, I get a completely different acceleration. Because if I apply that same torque very close to the center, then it's the same force, but a much smaller radius. That creates a much smaller torque, okay? So the only time you can use F equals ma on a wheel is if I literally just throw it. It's like, Louise, catch, okay? So if I throw this thing, I can use F equals ma. But if I'm making it spin, I can't use F equals ma, okay? Because where you apply the force alters the torque, and the torque alters the acceleration, okay? Now, I'm going to completely contradict myself, but stay with me here. So, we just said that torque equals force times radius, and we said F equals ma. So this is where I'm going to completely contradict myself, and I'm going to substitute ma in for radius. And sit there and go, but Mr. Burkamp, you said we can't do that. You're right, I did. I said we can't do that. But stay with me here. So A is your linear acceleration, okay? But a lot of times we're going to make it spin, but we're not going to have any linear acceleration. We're just going to have angular acceleration. So what's the relationship between linear acceleration and angular acceleration? A equals what? Our fish, okay? A equals our fish from yesterday, right? So I'm going to substitute m times our fish times r. Okay, just a simple substitution. Now I have it in terms of angular motion. But I'm going to rearrange this a little bit. I have r times r, which is going to get me what?
R squared.
R squared. So this is going to be mr squared times fish equals torque. Okay? But what does mr squared equal?
The thing we talked
Inertia.
about.
Moment of inertia, right? Capital I. So torque also equals I fish, and it equals force times radius. Okay, so torque can equal two things, force times radius and I fish. Now, let's look at this. If this is going to work, do both sides have to end up in the same units? Yes, because if they don't, we're dead in the water, okay? So you have force, which is going to be measured in newtons, which is going to be kilograms meters per second squared, right? Old school, kilograms meters per second squared. Then I'm going to multiply that by radius in meters. I'm going to get kilograms meters squared over second squared. Cool with that? Got that? Nice. Now, over here we have moment of inertia. What is every moment of inertia equation measured in?
Mass and radius.
Kilograms meters squared, right? Because it's mr squared, it's mass times radius squared. So alpha, though, is measured in radians per second squared. But radians are like this dimensionless number. So to multiply this by, technically, radians per second squared, but the radians really don't count because it's a dimensionless number. So when I do this, notice on both sides I get kilograms meters squared over second squared. Okay?
Oh, you know
So
what that looks like?
both sides produce the same units. They look completely different. You're multiplying completely different things together. One is a moment of inertia, and the other one is angular acceleration, and this is force and radius. They're four vastly different quantities, but you end up with the same units, so they're representing the same thing. So here's our bicycle wheel, right? So here's my bicycle wheel. Where is most of the mass located on this wheel? Towards the inside or towards the outside? Towards the outside. So this is going to have a relatively big moment of inertia because it's got all this mass located out here towards the outside. So when does it have a bigger moment of inertia? When it's at rest or when it's spinning? Or does it matter? Doesn't matter. Whether it's spinning or not does not impact the moment of inertia. So if you look at this, the moment of inertia for this wheel is going to be some value. Okay? I don't know what it is, it's just a number. It's going to be a value. So again, this is why you can't use F equals ma. So if I apply that force out here towards the outside, and I multiply that by a big radius, that's going to generate a lot of torque. Okay? It's going to generate a lot of torque because I'm applying that force way out here on the outside. But that has to equal I fish. So if this generates a big torque by applying that towards the outside, the only way that can balance out is if it generates a big angular acceleration. Okay, so if I apply that force out here, I get a big acceleration. Okay, and the same thing is going to happen if I go to stop it. If I want to stop it, I apply that force out here. Cool. Now, if I apply that exact same force right here close to the middle, I have the exact same force, but then I'm going to have a small radius. So I'm not going to generate as much torque. Well, I'm not going to change the moment of I, so if that happens, then I know my angular acceleration has to be a smaller number. So this is, again, if you're talking about objects that spin, you cannot use F equals ma. Because where you apply the force completely alters your angular acceleration. Okay? Got it? Good. Great. All right, one last big idea. And this is angular momentum. So, angular momentum is L equals I omega, or L equals I but, depending on what you want, how you want to play this. Now, here's the story. If you look at linear momentum is mass times velocity. Angular momentum is I omega. And they look completely different, okay? They look completely different. But at the end of the day, it's the same concept. So, moment of inertia is the resistance to a change in angular velocity, okay? How easy it is to speed up or slow down. So you're taking a measure of resistance of change to motion, and you're multiplying it by how fast something is going to spin. Okay? That's it. Linear momentum is mass, which is a measure of inertia, and you're multiplying that by how fast it's moving. So you're multiplying together two values that intrinsically are the same thing. You're measuring a resistance to change in motion by how fast it's moving. Okay? It's the same thing. It looks completely different, but it's fundamentally the same idea. So if you look at the value of I, so the units here get a little bit weird because that's kilograms meters squared, and then you have omega, which is like radians per second, okay? So the units get a little bit wonky. There's no like cute way to do this. It's kind of like kilograms meters squared per second, okay? That's kind of it. There's no kind of cute way to do this. Now, just like if you're going to change momentum, force times time equals change in momentum, right? We talked about this extensively. Force times time equals change in momentum. That's your net force, right? Remember, that's your net force. So here's the story. So if I want to make this spin, what do I have to do? Because it's not going to spin on its own. What do I have to do? I have to apply torque, okay? Now, what are the factors that determine how much the value of the torque is valued at? There's two things that determine the value of that torque.
Mass.
No. Torque.
Force and radius.
Force and radius. How much force I apply and
The rate.
how far out I apply it. Now, what's the initial angular momentum of this wheel? Zero. Does it have a moment of inertia?
Yeah.
Absolutely. It has mass and it has a radius. But it doesn't have any angular momentum because it's at rest. Just like this apple has inertia, but it doesn't have momentum until I make it move. This has moment of inertia, but it doesn't have angular momentum because it's not spinning. So, let's say that I apply a small force out here, but I only apply it for like a short amount of time. That doesn't create much change in momentum. But if I apply that force over a much longer period of time, that creates a much bigger change in momentum. So it's the same idea. Force times time equals change in momentum. Now, with a change in angular momentum, that's the torque multiplied by how long that's applied. Okay, now let's look at the units. So we said torque is Newton meters, right? Okay, newtons times meters. Torque, force times radius. Then you have time, which is going to be in seconds. Now, but newtons are kilograms meters per second squared times meters, right? Okay, Newton meters times seconds. Well, That's gonna get you kilograms meters squared, and I'm gonna cancel out one of those, and I'm gonna get kilograms meters squared per second, which is the exact same thing that you get when you calculate I times omega. It's the exact same thing. You get kilograms meters squared per second. It's the exact same units. So what this means, okay, that change in angular momentum is, and this should make sense, the bigger the torque that I apply, the greater the change in the angular momentum. The longer that I apply that force, the greater the angular momentum is going to change. So if I get this thing spinning, and I just touch my finger here for just a small amount of time, and I don't push very hard, I don't change the angular momentum very much. But if I apply a lot of torque, by applying a lot of force, I change that angular momentum a great amount. Now, so here's the last big idea. You have two great conservation laws when it relates to momentum. One is conservation of linear momentum. Linear momentum has to be conserved, right? So this is why the two carts on that lab that I just gave back, when you release the spring, they had to go in opposite directions, right?
Yeah.
Linear momentum has to be conserved. Guess what? Do you think angular momentum has to be conserved?
Yeah.
Absolutely. Caitlin, come up here. I need your help. So, Caitlin, before you go, spin that camera so that we can kind of see what's happening over here. I need to go get a 1 kilogram mass. Hold on.
I could have gotten it for you.
Well,
You getting your steps in?
I need the exercise. Okay, Caitlin, come up here. Caitlin's gonna stand on the green spinny thing. Okay, stand on that, kind of get centered, those arms out, hold that, hold that, hold that. Okay,
This?
like that, right, just hold it. So, Caitlin has mass, Caitlin has a radius. Does Caitlin have a moment of inertia?
Yes.
Because she has the two things that we need. She has mass and she has radius, right? Now the question is, can you change your moment of inertia?
No.
No.
Really?
No,
She
yeah,
can't change her
can't.
radius.
Yeah, she can.
Oh, like my radius in my arm?
Ah, so if you lift your arms out, what happens to the moment of inertia?
Goes up.
It goes up. Puts it down to her side,
Smaller.
smaller. So she can change her moment of inertia by changing her radius. Can she change her inertia?
No.
No, because that's mass and radius, okay? Excuse me, just mass. So she can't change her inertia, but she can change her moment of inertia, okay? Arms out, big I, arms in, small I. Got that?
Yes.
Okay. Now, right now, what's your angular momentum?
0.
Yeah.
0, why?
Not moving.
Not moving. Has I, but she's not spinning. So here's what I want you to do. So hold these up here. So I want you to take your arms and move those in one direction. Like that. Yes. Now, when she does that, do that again. If she takes her arms and moves them to the right, which direction do your legs move?
Opposite.
Opposite. Why do they move in the opposite direction?
Angular momentum has to be conserved.
Angular momentum has to be conserved, right?
Yes.
Ah. So if she takes her arms and moves them in one direction to create like positive angular momentum, which direction do her legs have to move?
Yeah, they're-
Opposite.
Opposite direction, so they still add up to 0. Okay? So this is why she can't take her arms and move them in one direction and have her legs go in the same direction. That would be like you releasing the spring on the cart and both carts go in the same direction. Okay? It's not going to happen. Okay. Now, I'm assuming you have a decent sense of balance.
Yeah.
Okay? So what I'm going to do is I'm going to apply a torque to Caitlin to get her to spin. Okay? And initially I'm going to have you with your arms out. Okay? So I'm going to change her angular momentum by applying a torque over some period of time. Okay? So once I get you spinning, then I want you to bring your arms in.
Okay.
Okay? All right?
Yeah.
Got it? Okay. Don't hit me. Watch that. Okay, you ready?
Yeah. Maybe push me fast.
No, now bring your arms in. Okay, now, as soon as she brought her arms in, well done, didn't fall. As soon as she brought her arms in, what happened?
I go faster.
Oh, why?
Her angular moment,
The
no, her
radius is
moment,
smaller.
moment of inertia.
Okay, so when she brought them in, what happened to the moment of inertia?
Got smaller.
Got smaller. Angular momentum has to be conserved though.
Yeah,
So L has to stay the same.
yeah.
So when I got smaller, what had to happen?
Velocity got higher.
she had to spin faster to produce the same
Velocity.
angular momentum.
Yeah.
Mm-hmm.
Okay? Now this one, I want you to like bring them in and like over your head like this.
Okay.
Okay? You ready?
Yeah.
But then I want you to put your arms back out. So do this,
Okay.
spin for a little bit, and then back out.
Okay.
Complicated, but I got faith in you. Okay, you ready?
Yeah.
Okay. And whoo, back out. Now, as soon as she put her arms back out, what did she do?
Slow down.
Oh, she slowed way down. Why?
Because the radius are
Radius got bigger, the moment of inertia got,
Bigger.
so therefore she had to slow down. Okay, now, I need you right here. Now, direction of angular momentum is complicated. Linear momentum is simple, okay? If the squirrel goes this direction, that's positive. If the squirrel goes this direction, it's negative. Okay, it's just positive and negative, that's it. Angular momentum is complicated because you have to use what's known as the right-hand rule. So, put your arms out. Okay, so if Caitlin is going to spin in this direction, okay, so here's how you determine the direction of her angular momentum. You put your arms down. So you take the right hand, okay, right-hand rule, and you put your thumb in the direction of axis that it's going to spin about. So she's going to spin about her center axis, okay? So you take your hand and you curl your hand in the direction that she's going to spin. So if she's going to be spinning in this direction, I put my hand like this, my thumb points up. So the direction of her momentum vector is pointing upward. Now, if I make her go in the opposite direction, I take right-hand rule, it only works with right-hand rules, then I curl my hand in this direction and her momentum vector is pointing down. Okay? So if she goes in this direction, the momentum vector is pointing up. If she's going in that direction, the momentum vector is pointing down. Only works with the right hand. Okay?
Caitlin, can you see what he's doing?
Because if you use the left.
But she can get an idea. Okay, now,
Yeah.
give me those back. We're almost done. Give me this. Okay.
Sorry, my hands are really sweaty.
No, you're okay. No, we're not done yet.
Like,
Okay, hold this.
I'm like, can't you tell what the right hand rule is?
I need the left and right tattoos, like the L right
Yeah.
here.
Okay. So, hold it out like this, up by the handles. Tilt it. Anything happen?
No.
Okay. How much angular momentum is in the system right now?
None.
None. Why?
Because no velocity.
There's no movement. There's nothing happening.
No,
Does the wheel have a moment of inertia?
indeed.
Yes. Does Caitlin have a moment of inertia?
Indeed.
Indeed. But there's no angular momentum.
Indeed.
Now, what I'm going to do, tilt it over like this. I'm going to get this thing spinning.
Okay.
Okay.
Pull it out or in?
Hold it out. Hold it out. You want to keep it away from you.
Okay.
And then I want you to tilt it over. And then I want you to tilt it back.
Okay.
Okay, you ready? Okay. Now, tilt it back the other way. Now, like all the way over. Okay?
Golly.
Now, tilt it back over.
Muhammad Ali.
Okay? So, when she tilts it, what happens? She spins differently, right? Now, hold this. Okay, now hold that back out like this. So, this is what's happening. Is that when I spun it in this direction. So, when I spun it in this direction, I'm going to take my right hand, I'm going to curl it this way.
Oh.
The momentum vector is pointing out this way. Okay? So when she tilts it, she changes the direction of the momentum vector. So she has to spin to counteract the changes in the momentum of the wheel. when you tilted it back the other way, your body spun in the opposite direction because the changes in the vector were reversed. So now, if it's not spinning and you tilt it, what happens? Nothing. That's boring. Okay, well, that was exciting. No, it wasn't. But if it's spinning and she changes that angle, she changes the direction of the momentum vector, she has to then have an equal change in her momentum to balance that out. Now, hold this out. Now, if I had spun the wheel like this, then I would wrap my hands in this direction and the momentum vector would point in this way. So your momentum vector always points at right angles to the plane of the spin. Why I call it the right hand rule. So if it's going this way, I put my hand like this, my momentum vector goes out here. If I go like this and curl it this way, my momentum vector is coming out this way. Got it? Good? Grand? Okay, thank you, dear. So, go with this back to Caitlin, she survived, and you can get her. Okay, so, if you look at what happened with Caitlin. So we started off, Caitlin had her arms out, okay, like this, boom, right? And so with her arms out, did she have a big moment of inertia or a small moment of inertia?
Big.
Big,
She had a big eye,
big, very big.
but she was spinning slowly. Okay?
She was
Now, when she brought her arms in, like this, what happened to the moment of inertia?
tiny.
So then she had a smaller moment of inertia, but then she spun much faster. Okay, hair went flying out. Okay, right? So to produce the same angular momentum, she had to spin
Faster.
faster. Okay?
That makes sense because, like, as a kid on the playground spinny things, you'd always like pull yourself in to go faster.
That's why.
Yeah.
Angular momentum had to be considered. Okay,
Oh, that's,
almost. Let me talk about the aside.
oh, it's purple.
Oh, it is purple.
Okay, so
Oh, wow.
the information that you're going to need up here at the top, I tell you, either you can use this or go to page 210 in your book. There's a more comprehensive list of moments of inertia. What's the only time you can use MR squared?
Point
Then
mass
who?
or then-
Point mass, then who? Only 2 times. Everything else you have to use a specific formula. Okay? So, when you get down to number 4, you have a solid cylinder. Mass of 3 kilograms, radius is 0.5, it's at rest.
Number 4?
Down below, we're starting on 5 through 10.
Oh, okay.
Okay.
Okay? 3 kilogram. Radius is 0.5, it's a solid cylinder. You need to calculate the moment of inertia of the solid cylinder. So if you look on a solid cylinder, that moment of inertia is 1/2 mr squared. Don't use mr squared because it's not a thin hoop or a point mass. So on number 5, you're going to start off by using 1/2 mr squared. When you get to the back side, when you get to number 16, you're going to calculate the angular momentum of the moon as it orbits the Earth. So I tell you, hint, treat the moon as a point mass. So imagine that I'm the Earth, and here's the moon going around us like this.
So we can use.
So you're going to use L equals I omega. What units does omega have to be in? Radians per
Second.
right? Radians per second. So here's the Earth, here's the moon goes around like this. As the moon completes one orbit around us, how many radians does it move through?
2 pi.
2 pi.
Oh, yeah, 2 pi.
And I tell you that it takes 27.3 days for the moon to complete one orbit as we go around. So to get your omega, you're going to have to take the 2 pi and divide that by the 27.3 days, but what are you gonna have to do with the 27.3 days?
We're in seconds.
Convert that into seconds. And then you have problems, and it's weird how the book did this moment of inertia and calculations. They're on two, it's actually out of 2 different chapters, which it's so weird how they did that, but this is the hand that we're dealt. So there's problems on page 222, and then there's also problems on page 279. On problems 34 and 35, give the direction of the momentum vector. You have to use the right-hand rule. So let me kind of give you another visual. So if this apple is spinning like this, I would point my hand in this direction, the momentum vector would point down. If the apple was spinning in this direction, I would curl my hand like this, it's going to point up. If the apple is spinning in this axis, I would curl my hand like this, the momentum vector would point this way. If it's spinning like this, I curl my hand like this, momentum vector points to my right. If it's at a 45-degree angle and it's spinning, then the momentum vector would be up like this. Okay? All right, I'm done. You're on your own. Be free. Have a good weekend.
Why does that happen?
What do you mean?
The right-hand rule, like, why?
It works. It's the universe that we have.
Who found it?
Huh?
Who made, like, who found that rule?
Oh, it's been known since we really started to study angular momentum.
Why is it the right one, not the left?
Because that doesn't match with the direction that the momentum vector points.
We haven't
So,
found out why.
we use the right, it's just like, why do we have mass? Why do we have gravity? Why does an electron have a negative charge? It does.
I think it's because of the electron.
Okay. Okay, then if you stop that camera,
No.
please do.